Okay. And then I'm also gonna, just as a backup, start recording on Bandicam as well. But that Bandicam, it doesn't anonymize. So I would have to basically either blur or cut certain places where your names are shown. So that's just something to work with as I go. Does everybody have any issues with the connectivity? You can also chat me if you don't like speaking in public or on Zoom. But it would be a good idea maybe to check in a little bit of visually. I'm not gonna force you to do that, but be mindful of that. It's actually good to show your face and do a face-to-face interaction with people, especially if you're kind of secluded online as you are right now. So that's a good way to cope with possibly being a little lonely or secluded, is to try to do face-to-face meetings with people a little more often. In class setting, it's a little awkward, I agree, but it's something that when you just walk into a class, it happens by default, and we take it for granted, but we need that for our personal well-being. So be mindful of that. If you're missing it, go on a video chat with your friends. Don't meet them in person just yet. So far, Austin is still on upwards trajectory. If you're in Austin, we are close to a very large port called Houston. Houston could be that whatever is happening in New York could happen in Houston as well. So be mindful of that. The problem with pandemic is that it's not the type of disaster that is very visible until it really happens. And so it strikes invisibly via germs, as opposed to some sort of a disaster such as hurricane that is very obvious, and it's it's easy to see what the disaster is, whereas in this case, it's kind of disaster in the waiting. And if you feel at any point that, we are doing this, and why are we doing this, and why are we secluded, it doesn't seem so bad. It doesn't seem so bad. That's the good news. Then the prevention is working as it should, but there is also a delay in it happening. So I don't know if I'm walking around with the virus. I don't know until I know. So that's something that we have to, since the widespread testing is not available, we have to walk around with that uncertainty. So please be patient, try to cope. Let me know if you have any issues coping. If I can help in any way. We're all kind of struggling in our different ways. What is bothering me about the whole situation might not be the same thing as it's what's bothering you. But we are all coping. So just be mindful of that and just acknowledge it and talk about it. It's easier to talk about it than not to talk about it. So I'm here if you need to talk about it and if we need to adjust. So one adjustment that I made is I did not post almost anything in these 2 weeks of spring break, essentially to let everybody cope with the situation and figure out what the new mode of operation is. Let me know if you're doing fine. Let me know if I can help in any way. One thing that I did immediately is I extended the request, I extended the deadline for the write-up, the first write-up that we're basically going to consider as a midterm. And that's gonna, I think I did that till next Wednesday or something like that, by a week. So basically, instead of this Wednesday, it's due the Wednesday after. So that's the first step. And I am going to, I didn't want, until this class restarted, I didn't want to post new homework. I'm going to add one more homework for segmentation that is going to be a little larger, or rather on 3, just a greater variety of methods than what we had that class exercise before the spring break. Okay. Can I continue? Did everybody have a chance to look at the video I posted last night? This morning, hopefully. Or did you have any issues?
Yes, I did. I saw the video, and at the beginning I wasn't able to see the video through the link that you sent on the mail. but then I found the video on your profile on YouTube, and I was fine.
Yes. So one thing that happened is that initially it posted on my private YouTube for whatever reason, because they're linked, and then it didn't show. And then I changed that. But if you follow the link in the initial email, if you get immediate emails from Canvas, depending how your Canvas settings work, then the first link didn't work, but I did change it. I edited it. So whatever is now on Canvas should be correct. But either way, it's now posted on the YouTube channel on the correct playlist. Did anybody else have issues? Yes, no? All right. Okay. So I'm going to assume that you have managed to do it. If not, you still have to. So I posted a PowerPoint where you can embed your solutions. I'm going to quickly show them. So basically, just a very quick summary is that we have segmented files now. We are not in grayscale world anymore. So when we still need to basically do certain corrections to segmented files, just like we had to, in a sense, filter our tomographic images. However, we have to do that both for the filtering purposes. Maybe there's some noise we want to remove in segmentation, or maybe we want to actually evaluate our segmentation and quantify certain things. So there are different procedures that we need to do in order to do that. And the very first one is quite a powerful two set of operations called erosion and dilation. And I'm actually just going to explain, instead of going through the entire video that I posted last night, I'm going to actually explain what it does on the set of images that were actually your little assignment. Let me just remove all of the files. So essentially, if you have, okay, minimize. Okay, okay, I cannot minimize. I can at least remove the lists. So basically, if this is my starting image, which is black and white, now depending how you choose to segment, what we are going to work with in this case is that and that's something that is set in process options settings, but we're going to assume that the object I'm interested in is white. And so that's called foreground, or the object. And background is everything else, which in this case is black. That could be reverted. So just be mindful that you have to kind of know what it is that you're working with. So if I'm working with white space as an object, so we could erode or dilate that object. If I'm eroding, I'm basically removing a layer of object. So my object becomes smaller and sort of the outside layer of it. Now, what's the exact size of the layer depends on what we call a structuring element that we erode with. And I think the default here in these operations is sort of like a 3x3 neighborhood. So basically, if you do that, so if you erode what is shown as white, which is pore space, you will see that that pore space has been reduced in this image. So all of these.
Excuse me, Professor.
Yes.
Yeah, maybe you can share your screen because we only
oh my
see
goodness,
the videos.
I'm sorry. I forgot to do that.
Okay, sure.
All right. Yeah, maybe I could do that, huh? Okay, here we go. Thank you. Make sure to make corrections like this. I've been talking. All right, so let's restart this. So this is the image, black and white image that we are trying to modify. And erosion and dilation are a type of modifications that are called morphological operations that are very commonly used. So this white pore space is my object. It's what we are referring to as foreground, or the object, and that's what I'm eroding and dilating. So if I now erode this white space, I'm going to get this result. You can see that it's smaller. And you can also see that in that process, these very small white spaces or object spaces or pieces that are smaller than that structuring element, they have disappeared. Okay? And that might be what we're going for if we're trying to clean something up. And then if I actually kind of go back and try to dilate back this object. So this is my result of this dilation. Okay? I can see that these small pieces, okay, have not come back, because once they disappear, I cannot now dilate them if they don't exist anymore. Okay? So now that I dilated my white space back, okay, after eroding it, so after peeling a layer off, I have added a layer, but that layer cannot be added to those portions of pore space that have disappeared. Some of them haven't disappeared, like this speck right here, and that one has come back basically full size. Okay? One thing that I also noticed that in this procedure, so there are certain artifacts to this procedure. One thing that happened is that these small specks, if I was looking to remove small pore spaces that are smaller than certain structuring element, I have successfully done so here. However, one thing that I have to be mindful of is that here, this and this sphere during dilation have merged. And now I cannot erode and make it necessarily disappear because this merger was pretty thick here. So that's simply an artifact of the procedure and cannot necessarily be avoided. Okay? These were merged to begin with. They have gotten a little thicker during this connection, got a little thicker during the dilation, and it did not get back to its initial thin self after erosion. And that's, again, artifact of the procedure. So one thing to understand that it's not reversible. You don't erode and dilate or dilate and erode and go back to the original state. Certain features that are smaller than that original structuring element that you're working with disappear. Okay? Now, if I actually do the opposite, so I basically initially dilate this white space, then I'm going to have these specks widen. And then if I basically go back and erode after dilating, I'm going to go back to this. Now, what has happened in this particular case, for instance, we have this speck here, it has connected with this space. And this one also has connected. So it's not a disconnected portion anymore. And basically, we have to also understand that if I'm eroding white and black space, just like in porous mediums, solids and pores, or if I have fluids in the pores, it doesn't matter. All of the phases, they're competing for the same chunk of space. So whatever I do to one, I'm doing at the expense of the other. So essentially, if I'm eroding one, I'm dilating the other, and the other way around. So basically, these are certain equivalent. When I'm eroding my white space, I'm actually dilating my black space. So that's essentially something to understand about these operations. But either way, when I'm basically, when I'm eroding, then dilating, I'm going to remove portions of the object that are smaller than, and that can be beneficial. So those are the, and you can look at the differences. That's what I requested you to do a difference between these images to actually see the difference. Let's now just do this as a exercise in 3D. Oops. Is this the correct one? No, I don't think that's the one I had open. Let me just go to the actual one. Okay. All right. So now we will go to the 3D example. So we can also do this in 3D. So I just want you to do this. It's a little harder to see, but it is important to do a 3D exercise simply because that's what we're gonna do. So try to follow with me. There is a 100 by 100 by 100 8-bit image, and you can duplicate this stack of images. And then we are gonna have to go to dilate and erode in 3D, and this is part of what I want to repeat the exercise in 3D. If you do dilate and erode that we did from the process binary menu, that menu is a 2D menu. So whatever you do is gonna actually process things slice by slice in 2D, and that's not equivalent to a 3D operations. If you have a 3-dimensional object, you want to use 3D morphological operations. So let's get going. Please work with me. So open, and we're gonna have to import image raw and go to the box. In my case, it's sitting in the box. Wherever it is that you downloaded this data, please go there. No, that wasn't short. It doesn't matter actually. Sorry, I'm talking to myself while I'm searching for data. No, apparently I do have to go to the other one. Okay. One shared. Yeah, that's the one. And this data is 100 by 100 by 100. And it's 8-bit. All right, it has been read in correctly. You can do a plus to get a larger size. You can walk through it. So this is one portion of that image, and you can see that these are I captured the portion of the beads that has small imperfections, and that's what you're seeing. So this was basically, some of these beads are actually indeed not perfect, and one would want to possibly remove that. So now, basically, to do this dilation and erosion, these are plugins that have been implemented separately from the ones that I showed for 2D. This is something to actually simply know about ImageJ or Fiji. It is open. In original version did not have 3D. Somebody else programmed this 3D and added it as a plugin, which is now pretty widely accepted. But that also means that it works ever so slightly differently than those 2D. So basically the same options don't transfer here. You go to plugins, process, and let's say that we want to erode. You then tell it which value, what is the object you want to work with, which in my opinion is actually much more clear than that other menu. So I say 255, those are my white pixels here. So let's say that I want to erode this white space. This is okay. And then I'm just basically, I can see that it has reduced in size. Okay. And you can repeat that number of times if you'd like to. So if I really want to kind of get rid of one of these, I can actually just go and do it again. So I'm gonna go and do it again. Okay. And now I can see that the majority of them has disappeared. This one persists. And I'm gonna, for the purposes of this, I'm gonna say, okay, I'm happy with this. And then I'm gonna dilate things back twice to hopefully go back. So, okay, plugins, process. Again, you can choose to do it 3 times if you want to. This is part of where it's up to you, and you devise a way to figure out, okay, when it is that you're happy with the change and what it is that you want to remove with it. So I'm gonna dilate. Okay. And I'm gonna do it once again to presumably go back to the original. Okay. So now I can see that there's that big one that is still back. It's more rounded than it was, by the way. So some of these speckles haven't been removed, but I can also see that these necks have gotten thicker, and that's something that is an artifact of this procedure. I'm gonna wait a little. Tell me if you're okay. Have you managed to do this?
Yeah.
Yeah?
Yeah.
Do we know how to basically now go and see where the changes have been? How to subtract from the original, or do that X, or was that clear?
Yeah.
So basically, you can come up with a number of mathematical operations that will tell you what the difference is from the original. These are stacks of numbers. Now, in this case, it's 0 and 255. You can go and add 2 images, and you will see where you had both zeros, it's going to be a 0. Where you had in one of them 0 and in another one 255, the result will be 255. And where you had both 255, you're going to have a result of, what is 255 times 2? 510. So you're going to get a stack of numbers that you can then process and analyze to see where the differences are. But that XOR, exclusive OR, I find pretty useful because it gives you basically just where the differences are. Where do these things differ? And this is where we would see these thicker things. So you just do it in 3D on the entire stack. Okay. And basically, let me go back to the presentation. I hope you still see my screen. I'm gonna have to move this away. Excellent. So basically,
I have a quick question. So when we erode and dilate, how can we be sure that we are not affecting the properties that we're going to measure? For example, if we are going to measure here porosity or something, even after we erode and dilate, there's some we see that some grains are still getting connected. So
yes, so porosity is just a number, and you can test how you're affecting that number, right? However, porosity doesn't tell you how things are connected.
Yeah, I know. I'm just saying here visually, when we're seeing the grains and how they're like visually after eroding and dilating,
Yes.
like
So,
some of them that were originally disconnected are now
connected.
Yeah.
What I like, and that's actually going to be our one of the next exercises, is finding connected components and seeing what the largest, like one way to monitor is seeing like what is your largest connected component doing. One thing that I like to look at is I typically do this for removal of small features that are smaller than a structuring element. You do have to first decide what is small for you. Okay? What are the small speckles that you want to remove? Now, there are 2 things. In this case, probably some of these holes that are seen inside the beads are actually real. They're just not necessarily something that we can access if we are thinking about fluid movement. So we don't care about them and we can remove them. Some of them are actually effect of the resolution that is not as high as we would need to. So, and combination of segmentation as an algorithm, which is not perfect, and resolution. So there are certain connections, for instance, between two, like if you have a very thin neck in between two things, whatever it is that you're imaging, that thin neck might not actually exist there in the segmented image simply because it's too thin. So you will get that it's a segmentation artifact that these two things, like there is a small speck that is disconnected from the large one, right? And that disconnection is actually a segmentation artifact. But it's just the reality. We have finite resolution, and that's what it is. So in that sense, if you're thinking about flow, having a small speck of solid sit in the middle of the pore space is not physical. I mean, it's either moving or something, but it's not going to just be there. So you want to remove that speck, and you just want to kind of convince yourself that by removing it, you're not affecting a large portion of pore space or space in general. So I would basically, when removing something, just check what is the effective change in porosity, and then also check connectivity. And we're going to do this, it's called find connect components, that basically checks connectivity. And those are two important things. You do want to remove small features, because small features, if whatever simulation, and we are typically doing this for simulation, and this is in part while I'm spending quite a bit of time on it. First part is characterization, just like evaluating porosity. And you want to be sure that you're not changing numbers very much. But you also want to improve your simulation outcome. And if you have too many small things, it's just noise. Good luck simulating in anything that looks like this. It's not going to happen. I mean, most of the simulators will not converge, will bomb on you. So even if it's, I don't know, real, it might be real if this is actually real microporosity and not noise. That just means that your image was not good enough and you shouldn't be simulating on it, or you should simulate on some sort of a smoother version on it, in which case reality is relative. Does that answer your question, or does it confuse you more?
Yes, it answered my question. Thank you.
So part of it is like you have to turn on your judgment, and you have to decide how you're going to judge. One effect on it would be, if you're interested in flow after this, then you go and test what's the change in permeability. That's your ultimate test. And does whatever it is that you get, however you post-process, pre-process, post-process, how you basically both filter and segment and then filter again, you get an image and then you simulate with it that something should be close to reality, with the understanding that the number that you're, in terms of permeability, comparing to is likely on a larger scale than your image, because it's a lab measurement. So there is quite a bit of uncertainty in the procedure, and that's just what we have to deal with in general in porous media. Yeah? So, and all of this also depends on what it is that you intend to do with the image and what it is that you're trying to do after. So your post-processing for different applications later might be different. So some of them might just survive. Frankly, if you're just measuring porosity, that noise that is relatively randomized, it's not random, but it's randomized, this type of noise does not affect porosity as a number all that much, because it kind of equally works. These misidentified black pixels inside the white space and misidentified white pixels inside of the black space, I could convince myself that there's kind of, they balance each other out. So if they do, your porosity number is not going to be all that far from what it actually should be or what it is. So if all you're doing is measuring porosity, then you're okay. But if you want to measure permeability using this image, boy, you're in trouble. So that's the type of, so it does depend what are you doing afterwards with the image compared to what you had before, to basically judge whether it's correct or not. Okay, all right. So this is one example of this exclusive OR that gives difference between you can see these necks between the spheres that are thicker than they were, and there's these small holes that were filled inside the beads that are also the difference. So you can evaluate how much of these, how much space do they take, and if it's a relatively small change. For instance, these necks near the beads, they're not going to affect permeability much if you're measuring permeability. However, if you're doing some sort of solid transfer, then this thicker neck will affect the mechanical property of the solid phase quite a bit, because transfer actually happens through these sphere contacts. So if now your sphere contacts are suddenly twice thicker than they were, that's a whole different set of measurements then. And likewise, in any kind of solid-solid transfer, these small speckles, whether they're there or not, it doesn't matter. So you do have to have the end goal in sight to understand how is this type of, it's actually a type of noise or change, how is it going to affect the ultimate result. Okay. I'm gonna skip this. So you can also filter simply, you can filter different ways. So if you just want to avoid creating these necks, you can just say, okay, remove all of the small stuff that is smaller than certain size. You can also do simply a majority filter, just like we did in filtering the grayscale images. It works, these filters kind of work the same. Median filter, same thing. It's just that they're working now only with two types of numbers, 0 and 255. So if you're doing median, you're just going to do some sort of a type of majority filtering on your structuring element. You're just going to evaluate where is this majority, are there zeros or 255, and they're going to set my pixel to the majority of the neighborhood. So it's just that I'm working with the binary type of image now, as opposed to an image that might have had a continuous change in numbers, and that's the only difference. Mathematically, they kind of have the same type of, the way they work is the same. Okay, so I see two people that have, let me just double check quickly. Two people have fallen off the video. Let me just see that I don't have any chats. Or no, or is it the, oh no, everybody's here. Okay, this is me getting used to this entire, let me do the wider stencil so I can see everyone. All right, excellent. Just making sure that we are still on the, okay, let's continue. So you can also do the median. So if you do the median filtering, you have to understand what is the type of neighborhood that it works with. By default, there's a median filter that works with 3x3x3 neighborhood, and that's in plugin process median. So basically there is also process filters. So 3D filters are typically these extra plugins that have been added. So in plugins, that's something that is separate from the mainstream ImageJ development. So they work slightly differently. The one in process filters median 3D, it works with that circular mask that we were looking into at some point when we were looking at these filtering operations. Whereas the one in plugins process median, it works with 3x3x3 neighborhood. So that's something to understand. So this is just to show you an example. If I had that original image, does everybody feel like trying this out right now? Majority filtering? How about we do that? So I'll wait for you to open that original image, or I certainly have to reopen it because I modified it. So this was the modification after 2 times. Let me reopen. Import raw. Okay. Okay. So I'm suggesting, let me remove this one. So I'm suggesting that you do plugins process median filter. In 3D. I'm gonna do it once. So some of these bigger ones have not disappeared, but I can see, I'm actually gonna, I keep suggesting in the slides to duplicate the image that you're working with, and I keep not doing it because me talking in parallel and working, something's gonna drop off. So I'm gonna, well, open it again. Raw. And I'm actually just gonna see this median difference between the original and median. Let me see this slice 50. Just a cross section is somewhat useful to look at. See, so this small stuff here has disappeared with this, but not everything has disappeared. So we can actually just see what the differences are. There's my main control. So I'm gonna do image. Calculator, I'm going to do XOR between this one. I hope that's the right one. Let's just quickly see then cancel. I'm gonna seal the name of this one. I'm gonna save it under a different name, just so that I'm sure. Just to make sure that I'm not working with the modified version. Okay. So now I'm gonna do calculator. And I'm gonna do XOR, and I'm gonna do the median. Okay. Okay. So you can see how small speckles near the edges have been changed, and some inside. So this is not a large change, but basically it does smooth the boundary. And I don't have these thick necks to worry about when I'm median filtering, which I do when I'm eroding. Did everybody get a chance to do that?
Yeah.
Okay. And if I do quick statistics on this, let's do analyze histogram. Yes. So I can actually see what is the fraction, right, of these 255s. So this is, I have 100 by 100 by 100, 1 million. So basically I have changed rather small. My zeros have remained still 99.5% of what they used to be. Oops. So I changed less than 5,000 voxels out of million. I can live with that. I have much larger errors and everything else than that. So this is not a major effect on anything. Yes? And again, if this is about permeability, I have changed the voxels that are near the boundary where the flow will be near 0, which you know from your transport phenomena class. If you impose no slip, then on the boundary, you're going to have a 0 velocity. So wherever you made this change, it's not a high velocity region. So these changes are not going to affect the permeability all that much, but they might actually make it the simulation way smoother if you smooth the boundary. Yes? Okay. Unless there are questions, I'm going to move on. Yeah. So if you want to really actually change or remove these holes, let's say that these holes in the beads are bothering you really a lot, and you want to somehow analyze those beads. One problem is avoiding this joining of these necks. And basically, so if you do this morphological closing 3 times or with the radius of 3, it's not gonna do well because they will kind of merge in a great way. So one thing that you actually need to do first before doing that is try to separate the beads. And this is an action, and this is something that we're going to learn in this lecture as well. So trying to separate the beads actually helps. If you separate them and then work on each bead separately, this is something called Watershed, then this operation actually works. So if you do majority filtering on these separated beads and then kind of merge them, then the hole, there's actually this large hole here that was filled successfully. It's not perfect, but it's way better than any result. So you might need to identify separate objects if you are bothered by objects being merged. And separation of different objects is, again, a topic that we're going to work on in this lecture. All right. And you can see these changed pixels in this operation. All right. So now we're going to move on to discuss a little bit of topology, because one portion of this is identifying essentially identifying connectivity. How are things connected? And topology is a mathematical area that basically deals with that. So it's basically a way to quantitatively capture differences between two complex objects, but I want at the same time, I don't want to be bothered by details. So for instance, in mathematical world, the detail as far as connectivity goes, whether you have a sphere or you have a cube, that's a difference in geometry of the surface. But topologically, they're not different. They're both this compact object, sphere and cube are, and as long as they're filled. And basically, topologically, there's no difference between those two objects. There is geometrical or shape, the surface shape difference. However, the topologically, they're not different. So there's many applications of being able to study topology. And in math, it's basically abstracted. But in applications, we can actually look at our granular materials. Do those grains have holes? Do I want to remove these cavities within the grains? And do I want to evaluate them somehow? If my porous medium was actually your bone, then you can look at these interconnections and see health of the bone. An actual erosion operation that we have just done in our images for bones, it's actually how bones erode as we age. As you're losing calcium, the bones will get thinner and thinner, and those connections will get thinner and thinner, and that's why as you age and you have osteoporosis, your bones might break because of that. So that simple erosion exercise that we did effectively evaluates how osteoporosis is going to proceed. It's a simple numerical representation of it. Likewise, in granular materials, if you think about dilating spheres, which is eroding the pore space. So if I had my spherical packing, if I erode pore space or dilate spheres, which is the equivalent operation, I can think of that as a cementation procedure. So it's actually a simple way to simulate cementation. And you can then, in each stages, you can basically add layer by layer, assuming that this cementation is the same everywhere. So it's you are adding equivalent amount of, or the same thickness of cement everywhere. Then basically this layer by layer erosion / dilation works as a cementation exercise. So that can, and you can then evaluate how the connections of the pore space, or how the pore space disconnects in the process, and how these spheres connect more. So this type of evaluation gives good insight. Now, this little video is what mathematically shows that essentially the coffee cup and the donut are topologically a same object in math, and in particular because I can actually create a sequence of smooth in math means continuously differentiable operations that basically map donut to coffee cup and back. Okay, so again, topology or abstractions in math is sort of famous for not distinguishing the two. But as long as I'm just interested in figuring out how does this object connect, donut and coffee cup are the same. Now let's define this connectivity and what does it mean in digital world. So I will just basically introduce definition. Since I did give you a little bit of work outside of this class, I will end it a little sooner. So I will end it at 1:30. So basically that will just allow me to do definitions right now. So in digital topology, let's look at first in 2 dimensions. So this is a simple image, and this simple image has 1 center pixel, and it has about 8 pixels around it for a total of 9. Now, if I'm thinking of pixels being connected, if they share an entire side, then this pixel and this pixel are connected, but this pixel and this pixel that share only a corner are not connected. So this type of connectivity where only these red pixels are connected to the center is called 4 connectivity or 4 neighborhood. Okay? So basically this is just definition of that. This is a digitized sphere, if you will, in this with this very small radius. So this is one representation of that sphere where I'm assuming that I'm connected only as a 4 neighborhood. If I wanted to add all of them, then I have to consider pixels that both share a side or this edge and a vertex as connected. And then all of these pixels are connected to this center pixel. And this is so-called 8 connectivity. Sometimes it's going to be labeled as 9 connectivity and 5 connectivity if I'm also counting the pixel in between. How does that matter? So let me just define 6 connectivity in 3D. Now in 3D, the difficulty is that it's hard to see. If I place boxes instead of every pixel, I'm not going to be able to see them. So I'm going to just represent my center black voxel with a black dot at its center. So basically, if I have a voxel here and a voxel right next to it, this is the center of that voxel. These two share an entire side. And these two share an entire side. So these red voxels are 6 voxels. They're sharing an entire side with the central voxel. Whereas when I move on to blue, there's 12 of them. And you can hopefully convince yourself, if you kind of look at it as your hands, you can place your hands hopefully as a as voxels. So you can see that the black one and the blue ones, they share edge, whereas black and yellow share only a corner in 3 dimensions. So if I basically assume that only red ones are connected to the black one, I'm calling that 6 connectivity. If both red and blue ones are connected to the black one, then I'm calling that 18 connectivity. And if all of them are connected to the black one, it's 26. And I have a total of 27, so I can assume the center connected to itself. So sometimes this is going to also become 27 connectivity. Questions about this? Okay, so how does this matter? Let's just look at this object right here. Let's say that I have 2 types of spaces, the blue space and the white space, that are sharing this volume. If I assume that white pixels are connected only in terms of 4 connectivity, so I have this A region and B region. Are these A and B regions connected or disconnected? If I'm assuming that they're 8 connected. Anybody?
They are connected because, like, through the corner.
Right. So if I assume that they're connected as 8 connectivity, then I actually really have one object. A and B don't exist as separate objects. So I'm counting it as one object. However, if I assume that they're 4 connected, then I have 2 objects. So I went from 1 to 2. They're smaller, but I have 2. So you can see how counting absolute number of objects can be a little bit relative. Which is correct way depends on what am I interpreting these objects as. Now, these A and B, they're separated, or so I think, by these blue pixels. And these blue pixels, are they forming a line or not? By line, are they one object or not? And what connectivity do I have to assume for them to be one object?
Well, same thing. If it's 8 connectivity, then they are connected to the corner. If it's 4, then they're not connected.
Right. So I have some decisions to make, and they're not always, it's not always clear what it should be. Now, if this indeed is a line, and this is a digitized line, I took an image of a line or some object that is actually connected, and I look at it, and I want to call it a line, then I should basically consider, when I'm counting something or characterizing something about these blue pixels, I should consider them as 8 connected in order to consider this a line. Otherwise, if I'm choosing 4 connectivity, then I'm going to choose this as, I'm going to count 4 separate objects and not one line. Okay. So you have certain, I like the way I kind of represent it. So if I also want to stop things from, if I'm basically, we're going to do a graphfire algorithm next time, if I want to stop things or block things effectively, then this line should be thicker, and I should thicken it in places where I could possibly connect these regions A and B if I want to somehow block them off. So which type of connectivity I consider for which type of pixels, I have to be careful depending on my application. It might have slightly different results. Also, don't get too upset if you're getting slightly different number of connected phases. What you should always normalize by is look at things as distributions. So let's say that you're counting objects like this. You should normalize them by their actual volume and look at things as statistical distributions rather than the absolute number. Saying that you have absolute number of this many regions of that and that is kind of difficult to look at. You should look at statistical distributions. So this is something that is very kind of specific for digital world. In continuous world, we would have a continuous line and we wouldn't be asking this question. But this is the result of digitization and working in this space. So I'm going to stop here today, and then we're gonna continue on Wednesday. I'm gonna try to kind of create just a very simple sort of digital quiz, if you will, on these connectivity issues before the next class. Okay? Everybody still out there?
Okay.
Yep.
Yeah,
Sounds
sure.
good.
All right. So again, I'm gonna post this as usual online. Again, as I learned, and I'm gonna double check right now, this Zoom recording should be anonymized. So whatever I post on YouTube should not have your names on it. And if not, I'll have to modify it. Okay?
Okay.
All righty. Well, I see you on Wednesday. Let me know if we need to discuss. Everybody knows what they're doing for their project write-ups?
Yeah.
Yes? So there are 3 of you that are working together. Bernie, Javier, Danny, you know how to contact each other, work together, all that?
Yep,
Yes,
yep.
we have a group where we're texting kind of things, but we actually wanted to talk to you. Maybe we can get like a insight on what we have
Sounds
to
good.
do.
Okay. Let me do that. So what is everybody's schedule tomorrow?
I have class 2 to 4.
2 to 4. I have a faculty meeting. Okay. I am going to anybody else has anything tomorrow
I have class at 9:30 to 10:30.
till 10:30? Danny, you good?
Yeah, no classes for me. I'm good.
Okay, so I'm going to attempt finding this. We'll have to tomorrow. I actually have to balance being childcare for my children, so this is going to be interesting. And I'm gonna try to set them up with a cartoon around 11. So tentatively, I'll send you a Zoom for 11 o'clock.
That sounds good. Thank
And
you.
we're gonna
That works.
have to potentially work with some interruptions, but oh well. Okay.
That's fine.
Dr. Marsha,
Yes. How are we meeting tomorrow?
yeah, we're
with
meeting
Christopher and
tomorrow at 4, yes.
At 4. Okay, I'll double check. I hope my faculty meeting didn't land in that spot. But
Okay, I
we're
mean, it should be
we're
4
working with
to,
new schedules.
right.
So I might need to. So I'll say Christoph is probably fine, right?
Yeah.
So I might need to move it to later when my husband stops working. Then I know he can handle children and we can actually talk. So I
Okay,
might
yeah,
move it to
whenever.
6.
Okay, sounds good.
So
Whatever
I'll
time
email
fits
you
for
about
you.
that. Yeah, it's a new balancing world.
I know.
So yeah. So oh well. We're gonna work with it. So this morning I actually have one of the children that is he has an infrared sensor for my movement, I swear. So I get up and within half an hour he's up and running and wants to talk. So this morning I got up to prepare the other lecture and of course he was up, so I have to work with that. Okay. Sounds good. I see you on Wednesday and some of you tomorrow.
Okay, thank you.
Mhm.
All right. Thanks.
And this is where I need to figure out how
Thank
to
you.
stop recording. Stop recording.